You still have to have a very good physical understanding of the world and be able to put the hardware together, so you have to have computer science, numerical modeling, and the hardware that can bring this imaginary world to the screen. The next speaker actually won 2 Academy Awards for this work, and the full, you see the Academy Awards on TV, and the full name of the Academy Awards is the Academy of Arts and Sciences, and you don't hear so much about the sciences part of what goes into Hollywood movie making, and that's what we're going to hear about today. There's a lot of very good engineering that goes in. So Joe Mancewicz is a senior software engineer at Nvidia's Omniverse unit. He actually started out in space physics at the University of Michigan. So for all the young professionals out there, this is just a good message that you never know where your career is going to take you. So really be open to anything that's going to come your way. And now he's here in Hollywood making movie magic. So I want to welcome to the screen Joe Mancewicz, or welcome to the stage, Joe Mancewicz.
Good morning, and welcome to Hollywood adjacent Pasadena. I have a few stories for you from my time in the film industry. I spent about 20 years in the visual effects arm of the film industry, meaning that we delivered computer-generated imagery and elements to feature films. Also worked on a lot of commercials and a video game here and there. But to kind of set the stage, I'm going to play for you what we call the sizzle reel. It's our demo reel. We would update it every year or two. It was a way of kind of letting potential clients know what we were up to and if it would be fitting for their films. If we had a lot of firework or smoke or water, they needed a film with that. This was kind of our chance to show them what we were doing. This is about a decade old, so it's going to look a little dated, but it kind of gets you the idea of what kind of space we were in. Okay, so there's going to be words that are going to want to fall out of my mouth because I've been doing this for so long, and if I say them, I want you to know kind of what I mean. I'm not going to go into deep anything. There are no equations. I was asked not to do that. But if I talk about a point, I mean a 3D position in space. Sometimes I'll call it a vertex or a group of vertices kind of thing. The edge connects 2 points, and then if you connect edges end to end, you end up with a strand like of hair, or a tail or a tassel or something like that. And that is an element. You can call that an element, but another element would be when you loop it all and you close it back around, you get a polygon. You color the face of that and you call that a face or a surface or a polygon. So sometimes I'll say element and I mean both of those things. A mesh is a collection of elements. So this is a model of the next line is going to be a model. So a model is a specific measurement. So you'd say I have a model of a cat, a model of a car. When you're talking about it in a generic way, I'll say a mesh or a surface or whatever. So in the audience, you're looking up at this green guy on the right, and you can kind of see there are blue surfaces and green, and I think you would guess that the blue surfaces probably don't deform. They're going to be rigid, hard surfaces. And the green parts are going to be soft surfaces. And you can see that it's all built up of triangles and quads and things like that. But the soft surfaces you would expect to be able to be deformed and move, like his arm can bend. And the way we would deform a character like this is kind of like we make a virtual skeleton within it. We bind the points to the skeleton with some kind of weighting. It gets very complicated. And then that would move the muscles and the skin. And that's kind of an understood problem. The other part of him is this loincloth he's wearing. When I started in the industry a long time ago, there wasn't a good solution for how we handled things like cloth. So if you had a character who was wearing a necktie, an animator would have to do all of the posing for that character to do whatever they're going to do in the scene. And then they would have to go through and try to make we'd have controls on the tie, so you can move them to different points in space, and say, how do we make this tie appear to be physically real? It is a tedious job, takes a lot of time, it never looks right, and it's not any fun. So how do you kind of solve that problem? Oh, and the worst part is that then the director the next day will say, you know what, I don't want that character to be walking to the water cooler, I want them to be skipping or hopping or whatever. So the animator has to redo all of the motion work, which they tend to like, and then do the tie stuff, which they dislike. So how do you solve that? And the way you make things look more physical is to use physics. And so we would take a mesh like this. Along all of the edges, you build virtual springs, or between all of the points on a polygon, you construct little springs. I think I had a whole lot of slides on the details of this. I decided to pull because it gets a little nasty. But then you can run a physics simulation on that, and it will start to act like cloth. And there will be things like how bouncy is it? You don't want leather to be very bouncy, and you don't want, or you have frictional coefficients. And if you're going to drag a silk scarf across a marble table, it looks different than across a concrete highway. So a lot of those kind of parameters will go into it, and we'll solve cloth for the scenario like this. So the animator can do their work. A different kind of technician, called a technical animator, they'll run the cloth simulation. So this is going to be a little bit of a case study going through one scene. So this shows you, it's kind of a twofer. You see a little bit of the cloth simulation stuff, but you'll also see kind of what goes into one shot and how we do it in the production pipeline. And this is from a movie called Night at the Museum. I don't remember if it's from 1, 2, or 3. Anyway, so there's an octopus that comes to life in the museum, and Ben Stiller is trying to get a bit wet because it's drying up. And so we start off in the production, we have to know what they want to see. So we start off with kind of storyboard or artwork to show, this is what the character could look like. So this is going to be the octopus, and there's different variations of it. Once they kind of iron that out and they say, yeah, we want to go with this look, we do a 3D model of it. Now, it's modeled in this kind of weird pose like this with all the straight limbs, because if you model it with all the curved limbs of an octopus and you try to straighten them, it's very difficult. Start with straight, you can make curved. Start with curved, it's hard to make it straight. And then we would do, sometimes we actually go to, for different films, we go to natural history museums and we talk with people, or we go to the aquarium and we meet people who can tell us about the animals, or just to get the photography. And then we start our own art department. We'll start doing work on how we take that model and how we're going to paint texture maps to go onto it to look realistic. Then we have more art of what's the characterization of the character? How does it behave? What does it look like? So the people who have to do this kind of work know what you're aiming for. So this is going to start doing a little bit of cloth work. There's some manual deformation stuff going on, and then there's also simulation. So on the left here with the tentacle, you can see how the little suction cups want to stick to the ground. That is all the simulation stuff. The arching of it is going to be manually animated, but then all of the secondary effects of how it moves and how it gets stuck is done synthetically with simulation. Okay, so this is the shot that this is all done for. When we're getting assets from production, so this is going to be done when they do principal photography. They do a clean plate. You'll notice there's these green screens on there that they're going to replace with paintings later on. And you start with a room with no elements in it so that you can, if you have to paint out something, say we want to get rid of something, this is the clean plate that you'll paint into place. So here's Ben throwing virtual water onto this octopus. Oh, it's going to be virtual water and real water. So you can see there's a water cannon underneath it, and he's trying to line up the frame to make it look as if he's throwing the water and it lines up. So clearly this doesn't look very realistic. I would think that this would be hard to construct as a person on set to say, this is what we need to do so they can do the visual effects later. Or we'll put a water cannon, we'll just get rid of it later. You can see a little on the green screened painting in the background how those two cute squares kind of bouncing around now. So you're starting to get an idea of when things are going to go into it. So now we've painted out the octopus that he was throwing stuff onto with the clean plate. And then we have tracking. So the tracking is a 3D, you can see Ben's got a little wireframe around him. The room has this kind of wireframe. This is where modeling a 3D mesh for the room and for him and for her, at least her, oh, no, not her. But if something has to interact with him, if we're going to cast shadows onto him or splash water onto him and have it be virtual water, we need to know where he is in 3D space so that we can react to it. Okay, so this is just primary animation. This is what the animator produces. When the technical person who came up with this simulation first did this, he did just synthetic kind of random motion and it looked amazing. However, the octopus is trying to spread the water over his own head, and so that's kind of why we have had an animator get into it. So this is where it gets interesting to me, and this is the technical animation part. So we take the animated tentacles that were done by the animator, and then we can make kind of by proximity, bind it to these little simpler tubes. The simple tubes were moving in the way that the animator had it, and then we run cloth simulations on this. So we treat them like they're cloth elements, and they know how to collide against each other, against themselves, and to act in a physical way. So this is the first stage of technical animation using a cloth simulator for this. So this kind of gets you can kind of see this light green tentacle draping over the red one. That is what this kind of gets us, is the self-collision and collision against other objects. And then you can take that and put it back onto the original animation. So you get a little bit, now his tentacles are slithering over himself, but it's on the hero or the renderable version of it. And then we have an effects department who's going to throw in water. And if you think about water, you can simulate it as droplets, as particles, but then you also need a fluid simulation. There'll be a little bit of fluid simulation happening on the floor in a bit. So he's throwing virtual particles that get rendered as water, like kind of splashy stuff, that gets incorporated with the actual water that was thrown out of the cannon. So there's a lot of work going into one shot. Now we're adding the little sticky elements. So the stuff where he's kind of slimy and kind of sticking to the floor. Again, another simulation, physics simulation. And now for lighting, they have to keep track of where the particles hit the octopus, and then you can see it's lighting up green, but it's an indicator of when they go into final render, that green area is going to be rendered to look more like a wet texture, which is not going to happen for free. You have to be explicit about it. So any place that's green now will look wet in the final comp. And then when we're doing our renders, and so we would do an offline render that could be very expensive, took a lot of time. And here we have 24 different elements coming out of the same render process. So rather than composite them all at one time, we would get different variations of like attributes of lighting that we could composite later and bring out more specular highlight, and we could make it more diffuse. And you can have all these sliders that you take the expensive part, but you just don't composite it all to the end, and then you can play with some sliders and mix it around to get your final comp. Oh, and roto. So roto is sort of like the tracking thing, but we're keeping track of where Ben and the actress are with the red 2D markup. And that is so that you can, when you're doing the final composition of the scene, say, I need to have Ben not being occluded by the octopus. So when you have the octopus in the scene, it would be on top of him normally, and this is to say, where it's red, I want those pixels that are his blue pants and his boots to be on the front of it. So you can see that's why he can be in front of the octopus, because it's just layers of images, right? Quite a lot of work that goes into like 4 seconds of film time. So the second chapter is on a movie called Life of Pi. I've worked on around, like I said, 80 films. This is, I think, my high watermark was this film. It was just before we kind of went through bankruptcy and, as Hollywood does. I think 2 years after this, I left and went to Nvidia. And now I'm doing a lot of the same stuff, but for a profitable company. Okay, so this is principal photography. This was done in wave tank in China. You'll see the red markers on the walls there. We're going to use that to recover where we think the camera was. So rather than we need to get a replication of a virtual camera where the real camera was. And this is a tried and true way of doing that, is to use those kind of markers to retriangulate where, how to reconstruct the camera position and motion. So this is a guy in a little boat. This is the actor who plays in the film. It's a movie about him and a tiger. I think it's kind of metaphysical, but it doesn't look that threatening. And then once we get done with it, it looks more like this, where we've added an ocean, we've added a sky, we've added a tiger, which is killing, I think, a zebra. There's an orangutan in there. So a lot of the film ended up being what we were able to contribute to it. I think someone did an analysis, and we were in 75% of the shots, our company. So this is an interesting thing, which you might not think of as a normal visual effect. Because not only are we adding the virtual ocean, but we're making the ocean more chaotic. We're making the boat ride more chaotic. The camera on the lower left says track. That's what we track the ocean, the boat to be doing in the wave tank. And then we actually, if you look at the kind of how dynamic the ocean is, we're creating the illusion that the camera is moving a lot to compensate for the ocean. It's very dark. It's a subtle thing, adds a lot to the movie, but I don't think anybody who's in the audience will say, oh, I bet they did that as a visual effect. And then we're just blending in, extending the local water with our water simulation, which is an ocean simulation. Different looks, different weather. Yeah. See if this one fires up. I'm not sure what that was. That was supposed to be moving. Hold on. Anyway, this was a rotating thing showing the whole loop of the sky, what the different environments could look like on the water. Now, this is kind of where I'm more interested. This is a numeric model. This is a water simulation. I don't know. I imagine there's a ton of people here who have done a Navier-Stokes work. Because I had done that in my grad school, when we started our water project at our company, we needed a water solution. I was the one to start that. It got evolved over a decade to an excellent water simulation software. So there's like the particles, you can see the kind of fine mist, then you have the ocean, and then you also have a lot of the splashing, which are all different elements that go through different simulations that need to integrate together. So then we have this tiger. So this is getting back to more cloth simulation things. The tiger on the left is an actual tiger. His name is King. He's, I think, in France. And so if you have a scene where you don't need a synthetic tiger, the real tiger is a lot cheaper to make. I mean, it costs a lot of money to make a virtual tiger. So if you can get away with some of your shots with a real tiger and a trainer, there. It's you know, it's a better way to go. And it saves a bunch of money, but we need to make our tiger look a lot like King. So the tiger on the left is King, ours is on the right. It's actually overlaid on top of it. So if you kind of look really closely, once his tail is up on the boat, you can see kind of two tails. It doesn't line up just right. I think once he kind of lays up, and also where his paws are, like his front paws, you kind of is a little bit of a tell. But it was just our proof that we, you know, how well can we match it? Oh, this is not our work. Don't judge us. This was from, we would sometimes, rather than get a storyboard on paper, we would get a virtual storyboard kind of thing to show what do they want the shot to look like. And they could actually do this in pre-production so that they know how to shoot it. And you'll see in a moment why. So here he's going to be fighting against the tiger with this kind of poker. But they want to film the boy and have it be realistic. So they have an actor playing a tiger, grabbing onto the pole, and the boy is yelling at the man in the blue suit. And you know, it's a little different than it's going to end up looking in a minute. But you'll see him, the man in the blue suit will swipe away, smack at the, yeah, so the tiger has to obviously smack at the pole. So they have to know all of those things ahead of time so they can film it and then we can add a tiger. So that's the sway, obviously. Okay, so this is our early testing for our tiger. Again, left and right is real and fake. We have virtual skeleton, we do a muscle simulation. Really the muscle simulation is just kind of to put muscles where they physically ought to be, and as they kind of, as the character moves, it will kind of flex or shrink. And it gives you something to either deform the skin by or also optionally kind of ride the skin over top of, so like we have skin sliding over muscles. Very good animator did this, the motion. I think that for me is a lot of the work, and then also the simulation. Skin, muscles, what do we got? Okay, so similar sort of thing. So we have like a muscle simulation for him getting up onto the boat. And hand animated, somebody did it by hand. They were copying what they saw the tiger doing in the original footage, and then this is their virtual copy of it. And then we have 3 different layers of skin. So there's a subcutaneous layer. And you can see his paws are separated a little bit. They're not actually part of the simulation, but we're doing a cloth simulation on that skin. So we animate, so we deform the skin, and then we run a cloth simulation to kind of give it a little bit more real effect. You'll notice that his belly, it stays kind of flush and flat. There's not a lot of wrinkling going on in his belly before his leg. And then we add a layer of fat, virtual fat, and then we go to this dermis layer, and you start to see a little bit more of that kind of wrinkling of his skin. His paws are still not being part of the simulation. And he's kind of got the triangulated mesh. And then we get to the 3rd layer, which is the epidermis, and doing a cloth simulation. So we have 3 layers of simulation, all kind of affecting, one being affected by the next. And it gives you this kind of beautiful, I love watching this clip because of how silky and kind of fatty his belly seems. And then this kind of shows another composition. I've seen this on YouTube a bit, but kind of fading in between the different elements. So on set, when they're doing principal photography, they have the big blue fake tiger so that he has something heavy to move his arm around. It feels realistic. It might actually indent his leg a little bit. And it just adds to the realism of how his performance is going to be. And then we paint it out and replace it with a tiger. You'll see here, we have a tracking skin of him as kind of this white tan version of the young boy. That's going to be used to cast shadows. And you can see, or to move the fur on the tiger. It needs something to collide against, and it can be that tracked surface. And also, it just stands out until the last bit that they fade in here is the shadow, and it really adds so much, and that's being cast against that virtual tracked boy, but it's not, we're not rendering anything about the boy, we're just rendering the shadow that would have fallen on that. And it just stands out like a sore thumb until they get that last little bit, and when the shadow fades in, then it becomes believable. Okay, so refraction problem. We had a movie, I can start talking about this, I can play it a little bit. So the lenses on your eyes distort where your iris and your pupil appear to be, and if you have a cat, that gets really exaggerated. And we had a movie, I forget if it was Lion, Witch, and the Wardrobe, but we did a lot of stuff with cats and creatures that have very large lenses on their eyes, which will distort the pupil and the iris where they appear to be. And we had a movie where it was a close-up shot, and so here I've modeled the pupil and the iris as just a flat disc. You can kind of see the curve of the lens in front of it. And this is how it would appear in animation software. You don't see any of that distortion by default. Well, at the time, at all. You couldn't see, there was no way to see the refraction deformer, or refraction deformation. So an animator would deliver this, and with it flat, and the director would say, yeah, that looks perfect, render it. And the render is that offline render, it's very expensive, it takes maybe overnight. Come back the next day, the director sees that. And they say, why did you move the pupil and the iris? It's like, well, that's refraction, that's gonna happen. And nobody's happy about that. And then you have to go through this very painful iterative process of trying to fake the eyes to look in a different direction so that when it does render, it looks in the right direction. And it's got very expensive. So in order to try to save the hassle, I created this deformer, which deforms the geometry to make it look like it had been refracted. And we actually ended up using it kind of as a default thing for a long time. And then you just turn it off before you render, do the offline render, and so you don't double refract it. So conventional refraction, if you imagine the camera's on the left here, the point, and the green line is the image plane. Like what pixel am I trying to fill here? The cast a ray through that plane, through the pixel, into the sphere. It would find a point on the sphere using refraction of, I'm not going to get into all that, it would bend the light a little bit, and it would strike up either the pupil or the iris and tell the color, what color do I have to make that pixel on the image? And that's kind of how you think about normal ray trace refraction. In this case, I don't have that. I have a different problem, which is I know where the ray needs to land. I know where it's coming from. I just don't know where it's going to intersect the sphere. And so the challenge here was to compute, knowing where the camera is and where the different points in the mesh are, where would that array that would hit that intersect the sphere? It's a tricky problem. There are potentially infinite number of solutions in some very rare case. There's potentially 0 solutions or multiples, or like some number in between. So you have to kind of condition your problem to know this is the one I'm going to probably want. And to solve this kind of problem, I imagine everybody here has read Feynman's QED book, but light will take the path that takes the least amount of time. And so it's going at the speed of light in air, but it's going at 3/4 of the speed of light in the lens. So what path do I want to take that minimizes the time? And it's a solvable problem, I guess, I should say, get off that topic. And so now I'm distorting the lens. You can see the refraction is happening on the left pane from that camera, but at the top, the camera on the right, the pane on the right, is looking down to show you just how much the mesh is being deformed to create the illusion of refraction. And that's about that on this. But the question is, why would I bring that up? Here is that I had done this, and then I was at a CubeSat conference with a friend of mine, just for his company. So he was going to a CubeSat conference, I just hung out with him for the day. And during a break, he was talking about a project called Cygnus that he was working on, where you have satellites at different altitudes that need to be able to, one satellite sends a signal to the Earth, it reflects off the Earth and goes up to another satellite. And at any given time, they have to figure out which of this constellation of satellites do they want to be communicating with, and where would the reflection point be on the Earth. And he has an algorithm that he felt was a little slow for that. It took several seconds to compute, and he wanted to be updating this more regularly, and thought it should be faster. And I said, that shouldn't take several seconds, that should be a few milliseconds, because refraction and reflection in this case are going to be really the same thing. And so I took my refraction algorithm, changed the sign, got rid of the fact that light goes slower inside of the sphere, and so gave him this algorithm that he could, I said, you can put this on your satellite. And this is kind of an illustration of the satellites going around choosing which other satellites they want to be communicating with at any given time. Now, whether or not he added that, if he used my algorithm for the satellite, I don't know. But it was really fun to come from visual effects, just be there as a kind of goofball guest, and have something to contribute potentially to this remote sensing project coming out of visual effects. And I thought that was a weird enough thing that you guys might get a kick out of it. And then there's a flux problem. A friend had a PhD student who was trying to solve a problem for CubeSats. This is a 1x1x3 CubeSat with solar panels all over it, and it has these wings with it that'll open up, and you could select. So they were trying to solve this problem of self-occlusion. Which of these solar panels are being occluded by the satellite's body itself? And so the PhD student was saying, I know the sun is over here. I know the satellite body is over here. How do I cast this line from this and do this, what they call projective geometry, to do Boolean operations to kind of dice up these solar cells and figure out what percentage of them are going to be exposed to the sun. And I said, yeah, it's a known field. Most commercial software does this. You are way overthinking the problem because your graphics card already does this for you for free. In visual effects, if I wanted to make something like this so I could select it and I wanted to pick solar panels, I would not render it like this for the viewer to see. The viewer would see it looks kind of pretty and it looks like a satellite, but in the background I would render it like this. I would render it twice, and I would never show the user this part. But I would identify everything I wanted to pick. If I wanted to pick, polygons I want to pick solar panels. Then I make them all different colors. When the user picks at coordinate XY, I say, oh, what color is XY in this background image? Oh, I know that maps to the 47th solar panel, and I can select it. It's a very common thing in the visual effects industry. So when he came to me with this, very complicated projective geometry, Boolean intersection problem, I said, this is what you want to be doing. This actually, this did end up in a paper. This got into a publication on optimizing solar panel flux for satellites. But it's a very easy thing to do, and it's almost embarrassingly easy. But you just have to know that it exists, and I knew that it existed. So it was a second time that I got to bring something from the visual effects field back into the remote sensing field. Now, I don't really have a story about this. I just love dragons, and it's a nice way to close. So again, you'll see like the kind of familiar stuff with the skeleton being animated, muscle simulation layer on top of it. Now, what I really like about this is in his neck, you kind of see this torsional distortion as he's, the kind of weight and the kind of flexibility of his body. In some of these shots, because he's going to throw fire, the technical animator added kind of veins that you could see pulsing fuel to its mouth, which I thought was just fantastic. Can't pick it up in this shot, but it's one of my favorite things, dragons. That's all, folks.